This is the second video in the topic on how does a hot air balloon work. In this video we're going to be looking at gravity, weight and air resistance. In this video we're going to be considering gravity, weight and air resistance. All objects on Earth experience gravity. Gravity is what makes objects fall when we let go of them. Gravity is a force. Later we'll be looking in more detail about what a force is exactly, but for now, a force is a push or a pull. Gravity pulls all objects down towards the centre of the Earth. We have a formula to describe the gravity felt by objects on the surface of the Earth. Because gravity is a force, we write this equation as F is equal to the mass of the object times the acceleration it feels due to gravity. So acceleration describes how quickly the speed or velocity of an object changes with time. So when I drop an object, not only does it start to fall towards the Earth, but it falls at an ever increasing rate. It falls faster and faster as it gets closer to the floor. So for the longer time it's been falling, the faster it's going. Now Newton came up with the law of universal gravitation. Newton said that it's not just objects that are attracted to the Earth. Any two objects in the universe are attracted to each other, caused by the mass of these objects. So Newton wrote down the law of universal gravitation. The law of universal gravitation can be written as F is equal to some constant, the gravitational constant, which is given the symbol capital G, and is equal to 6.673 times 10 to the minus 11 Newton meters squared per kilogram to the minus 2, times the mass of the first object times the mass of the second object divided by the square of the distance between the objects. Let's have a look now at how we can use Newton's law of universal gravitation along with our first simple equation, F is equal to mg, to calculate the acceleration of objects on the surface of the Earth. So the acceleration of objects on the surface of the Earth is given the symbol little g. So we know that F is equal to mg, describes the force felt by an object dropped on the surface of the Earth, and F is equal to g m1 m2 on the distance between them squared is the force felt due to gravitation of any two objects which are attracting each other. So when we're dropping an object on the surface of the Earth, this mass 1 is the Earth and this mass 2 is the object. So what we can do now is equate these two forces. They're both describing the same thing, the force felt by an object when it's dropped on the surface of the Earth. So we've got that the mass of the object, this is the object, so let's call that MOG, is equal to the gravitational constant times the mass of the Earth times the mass of the object over r squared. Now r squared is the distance between the two masses here. So in this case, it's the mass of the Earth, here's the Earth, and we can imagine that all the mass of the Earth is concentrated at the very centre of the Earth, and here's our object being dropped just above the surface of the Earth. So the distance between the centre of the Earth and where we're dropping the object from is just the radius of the Earth. So this is the radius of the Earth. So you can see with these two equations, the mass of the object appears on both sides. So we can actually cancel that one out. And so now we've got an expression for little g, the acceleration due to gravity on the surface of the Earth. G is equal to capital G times the mass of the Earth times the radius of the Earth squared. And so this lets us calculate little g on the surface of the Earth, but we can actually use it on any planet we want. If this was Mars, we could put the mass of the Mars and the radius of the Mars. So let's just check that it works for the Earth. This is equal to 6.673 times 10 to the minus 11 is our universal gravitational constant, times the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, over the radius of the Earth, which is on average 6.37 times 10 to the 6 meters, and then we need to square that. So solving this on the calculator, we get 9.83 meters per second. And when we actually measure the acceleration due to gravity on the surface of the Earth, we do get 9.8, so that is in agreement. So if you ever need to calculate the acceleration of any object on any planet or on the moon, you can simply use this formula here. And to get the weight force of the object, we can simply use this formula here with the little g for the specific planet that we're considering. Okay, so we've said that F equals mg and little g is fixed on the surface of the Earth, which is saying that all objects should accelerate the same rate on the surface of the Earth. So they should all fall together if we let go. Now, this is true for relatively heavy objects. If I drop these two balls, which are not identical, one's a rubber ball and one's a happy sack, if I drop them from the same height, we should see them hit the floor at about the same time. Okay, so let's try that. So they hit the floor at approximately the same time. But what happens when I drop a heavy object and something which is really light, like this leaf? You can see what I said before clearly isn't true. They're not hitting the floor at the same time. So what's going wrong with the physics in this case? Well, the answer is air resistance. We've got air all around us. Air's made up of little particles, and these little particles try and stop the motion of the objects through them. So air resistance actually provides another force, and this force works to oppose the pull of the gravity. Air resistance is more significant the lighter an object is. So air resistance affects this leaf a lot because the leaf has a large surface area and is very light, whereas this ball has a slightly smaller surface area and more mass. So the gravitational force is larger for the ball because the gravitational force is given by mg. The gravitational force is smaller for the leaf, and so the air resistance is more significant for the leaf because 1, it has more surface area, and 2, it has less gravitational force to overcome. So these do not hit the floor together. But what would happen if we could get rid of the air? What would happen if we dropped two objects on the moon where there is no atmosphere? Well, on the moon, the leaf and the ball would drop at the same rate. Now, don't take my word for this. We're going to do a demonstration now to prove that on the moon, the ball and the leaf would fall at the same rate. What we have here is a Perspex tube from which we can remove all the air. You can see the patty case and the ceramic ball down the bottom. The patty case is very light and has a large surface area. The ceramic ball is heavy and has a small surface area. The air is removed by attaching a vacuum to this tube at the top. Okay, let's look at what happens to this cupcake patty case and the ball in a vacuum when we turn this tube the other way up. We'll replay that in slow motion now so that you can see exactly what's going on. You can see the patty case and the ceramic ball hit the bottom of the tube at almost exactly the same time. You can see that now that they're in the vacuum, they fall at approximately the same rate. Now what we'll do is we'll let the air in and see how that changes it. Okay, so now there's air in this tube. You can see now the patty case was a lot slower than the ball. And so around us, we've got air resistance. So F equals mg is correct, but it's only an approximation. In reality, things with a large surface area that don't have much mass are affected by air resistance. A hot air balloon needs to overcome this gravitational force to rise into the sky. So in the next videos, we'll be looking at how the hot air balloon overcomes the gravitational force, which is pulling it back down to the surface of the Earth.
Now, one interesting thing which happens with air resistance is that everything feels a weight force downwards. So we've got an mg force downwards. Now, the size of the air resistance force is actually dependent upon the velocity of the object which is falling. So here we've got a cat falling from a high-rise apartment. It wasn't pushed, it fell by accident. It feels an air resistance force upwards. Now, when it starts going fast enough, this air resistance force is actually equal to the weight force. So at that point, when the air resistance is equal to the weight force, it stops accelerating, which means that this cat actually starts to fall at a constant velocity. So this velocity is called the terminal velocity of the cat. And no matter how long the cat falls for, its velocity won't get greater than this terminal velocity. So they actually did a study of all the cats that had fallen out of their apartments in New York. And they found that the highest mortality rate for the cats was for cats which had fallen from the 7th floor. So the belief was that cats will reach their terminal velocity when they've fallen 7 floors. If they fall from higher than that, then they fall for a greater time and the cat has more time to relax in the air and to get into a suitable position to land. So cats have actually survived falls from the 45th floor when they've landed in flower pots. But the 7th floor is the most dangerous as they get to their terminal velocity and they have less time to prepare to hit the ground. So velocity is just another word for speed, except that velocity's got a direction as well. We'll be looking at that in more detail in a later topic. But what we can actually draw here is a speed versus time graph for the falling cat. Now initially it's got a lot of acceleration, but the air resistance force increases as the speed increases, and so the speed of the cat looks something like this. And we've got, it levels off here at this terminal velocity here. Special thanks to Sebastian Frick for filming this and some help with the editing of it.